Hello chemistry students. In this next lesson, we're going to look at the solubility product constant, also known as Ksp. Now at this point, we've seen several kinds of situations of dynamic equilibrium. We're going to look now at another heterogeneous system that specifically involves the ability for, or the dynamics between dissolving something into an aqueous solution specifically. Okay, so let's start. That's something, of course, being a solute. Okay, so first example. So we're going to write, you're asked now to write the Keq expression, which we will learn that is something a bit different. Let's see if I can select a pen here. Okay, so Ksp, essentially, that just means Keq. We'll talk more about that in a bit, but Ksp refers to the solubility of that solute I just mentioned. Okay, so now lead 2 iodide is being dissolved, dissociated, and produces two ions here, the lead 2 ion and two iodide ions. Now it says to write the equilibrium expression for this. Now you know enough now at this point to be able to do that. So hopefully you can press pause and give that a shot. Okay. Otherwise, in just a second, I'm going to go back to the next, go forward to the next screen. Okay, so hopefully you've written your Ksp expression or your Keq expression for this, and it looks like this. So we see that according to the balanced equation, the dissociation of lead 2 iodide here, we have a 2 coefficient, which then of course means we're going to have a 2 exponent over the concentration of iodide, and just a 1, and not seen here, but a 1 for the lead lead 2 iodide ion. Okay, something else you might notice is that there is no denominator. Now we know that there shouldn't be a denominator because that denominator would be the reactant, which in this case is a solid. And we know that solids and liquids are ignored in our Keq or Ksp expressions. Okay, so if we think about what this means, the equilibrium constant for a solubility expression, which is your Ksp or your solubility product constant, that really just means that for the dissociation of a solute in a solvent, if the rates forward and the rates reverse are equal, that means you can't dissolve any more solute, nor are those ions going to crystallize in the reverse direction, which means this represents, Ksp then represents an equilibrium constant for a solution that has reached saturation. Okay? So let's continue with another couple of examples here. Here we have calcium carbonate. I'm going to draw an arrow here in a forward direction only. I know it should be in both, so if you like that will work. Okay, but just for the sake of space here, not following convention, we're going to do it this way. So we have one calcium ion aqueous. Okay, assuming this is dissociated, of course, in an aqueous solution, and we have carbonate, also aqueous, all in a one-to-one. So our Ksp expression then looks like this. Okay, now silver phosphate, similarly, if you want that double arrow, of course, this is not usually how it's drawn, but we're doing that now. We have a silver ion, right, and a phosphate. I know you're wondering, sir, you've missed something. I definitely have. Hoping that you see that I've missed that there is a 3 coefficient here. Okay, so Ksp is then equal to, oops, just the plus 3. This is a 3. Okay. That's it. So we have Ksp expressions for the two of those. Okay, now a few definitions here just before we continue to examples, to a couple more examples. When we talk about the solubility of a substance, that refers to how much of that solute can be dissolved for every 1 liter of solution. That's referred to as in units grams per liter. Now molar solubility or molarity, big M, that's moles per liter. Okay. Okay, first example here. And I'm going to switch screens over to solve this, but before I do that, let's look at the question. So the solubility equilibrium, or Ksp, right, for this heterogeneous system, is given to us here. Here, look, we actually have a Ksp expression, although that wouldn't be hard to figure out from the balanced equation. And we have a Ksp value of 2 times 10 to the negative 10. Now, this being so low, that can probably tell you something about the solubility of this salt. Pretty low. Okay, good source of a communication question right here. All right, so we're going to do two things. It's asking us to calculate the molar solubility, so that's going to be moles per liter, and then the solubility, which will be in grams per liter. Okay, notice there's no formula I've given you here, so we're going to figure this out using the factor label method. Okay, let's get on then to solving the problem. Okay, so first, ice table. Okay, so that's the dissociation of strontium fluoride producing strontium and fluoride ions. All right, all aqueous, important to write states here. Okay, your ice table. All right, so having gone over how to treat solids and liquids in Keq expressions, you know that usually what we've done is we just put a line straight through this because we know that this is a solid, and that's correct for sure. I am going to go back a little bit though, or rather I'm going to go back on this point and say there is a consideration to be made here, this kind of example. Although we are ignoring this for our Ksp expression, right? Ksp expression in this case, again, it's given to you, but it's not too difficult. Oh, I've missed something. There we go. Right? Notice we don't include the reactant at all because it's solid, but we're being asked for the molar solubility of strontium fluoride. So we need to know the molar solubility of strontium fluoride. So there is some consideration that has to be made to this column here. So completely ignoring it as we usually do, although not incorrect for this kind of question is, and I won't say much more until we get to that point where it's more relevant. So hopefully in context it'll make more sense. So let's finish writing this ice table. So initial concentrations are 0 and 0. Right, nothing's happened just yet. Then we do what we normally have done, not negative but positive, and then positive 2x. You add I and C, and we get expressions at equilibrium of x and 2x. Plug those into our Ksp expression. Remember, we do have a Ksp value. I'll go back to that. And we get x, 2x. Of course, there's a 2 here from that coefficient, so don't forget that. So we get x times 4x squared, which gives us 4x cubed. And then that small value, that was something, 2 times 10 to the negative 10. So 2 times 10 to the negative 10 from the question. So all we'll do here is going to divide both sides. I have that worked out. Divide both sides by 4, and we get 5 times 10 to the negative 11. Then we're going to cube root to solve for that. And we get an x value of 3.7 times 10 to the negative 4. Okay, and that's our molar solubility. And we are done. Not yet, actually. I want to go back to that consideration I told you about. So what you figured out is the value for x. So this is what we know. We know the concentration of strontium ion. Now, because we know the concentration of strontium ion, and because when we compare stoichiometrically strontium ion and strontium fluoride, we know that it's a 1-to-1 ratio. So if we know the concentration of this 1-to-1 ratio of this ion, because of this 1-to-1 ratio, then we know that the concentration of strontium fluoride is going to be the same thing. So we can say, since it's a 1-to-1 ratio referring to strontium and strontium fluoride, therefore we can say that the concentration of strontium fluoride is going to be 3.7 times 10 to the negative 4 moles per liter, and now we're done. Okay, so see how we've ignored strontium fluoride in our Ksp expression because it is a solid, but we had to go back to it because we, of course, are talking about the concentration of reactant. Okay, so that was A. That was A. Now let's move on to B. Now B, haven't gone over formula at all, but hopefully you've been taught, or if you've been in my class, I know for sure you have the factor label method, and I'm pretty sure we have gone over this. If not, let me know and I'll post a video. Okay. But we need to figure out, so the fact label method looks like this. All you do is you write down the units you need. So we need grams per liter. There's no formula necessarily for this. I'm sure there is, but I don't have that memorized. Let's just use the factor label method and think about it. So we need grams per liter. We've determined that we have a concentration of 3.7 times 10 to the 4. Units are very important. Make sure to write your units moles per liter. So this is what's given. Then you multiply by a conversion factor. Now this conversion factor will help you take care of the units. So you compare this set of units to that set of units. You want to keep liters, so you're not going to want to cancel out liters. What you do want to get rid of is grams. So whatever unit you want to get rid of, you put at the bottom, right? So they can cancel out. And the unit you want to keep you want to keep grams, you want to introduce grams, goes at the top. Now, looking at this conversion factor, this should remind you of something, grams per mole. That's molar mass. So I've looked it up just prior to this, and it's 108.62 grams for every 1 mole. This is the molar mass. Use a periodic table for that. Right now, this is a 6, not a funny looking 8, right? So you do that, units cancel out, put that into your calculator, and you get 4.0 times 10 to the negative 2 grams per liter of strontium fluoride. And you're done. Okay. So hopefully that has helped. We've completed A and B. Now last example. So here we have the dissociation of silver chromate. Now silver chromate dissociates in a 2-to-1 ratio. We get 2 silver ions for every 1 chromate ion. Now this question isn't asking you to determine concentrations or molar solubility at all. It's just asking you to figure out what Ksp is given 1.3 times 10 to the negative 4 moles per liter of silver. Okay, now if we have this concentration of silver, great, we have that concentration. Our Ksp expression looks like this. We have silver, we need to know what chromate is to figure out Ksp. Hopefully that isn't too complicated as you're looking at it, but if you notice, this is a 2-to-1 ratio. So essentially, whatever value you have here, it's just half of that for chromate. That's really all there is to it. So a bit of an explanation here. To figure out that chromate concentration, you take half the concentration of silver, so you half that, and you get 6.5 times 10 to the negative 5. Of course, this stands for moles per liter, molarity. Right, you have that value now, plug that into your Ksp expression given to you in the question, and you get, don't forget that exponent 2, 1.1 times 10 to the negative 12. That is your Ksp value, and that's it for that question. Not too hard. All you're using here are mole ratios and a bit of stoichiometry. Okay, here's your practice homework. Let me know if you have any questions. I hope this helps.